Hi everyone, my name's Molly. I'm an MJOL student at the University of Leicester, and my current research is on the applications of deep eutectic solvents to recover gold and useful byproducts. So traditionally, gold is recovered using cyanide as the reagent. Now there are a few environmental and social issues with using this. Firstly, the form we use it in is sodium cyanide, NaCN, which is highly toxic. Therefore, any mine tailings where cyanide has been used pose a threat to the environment as they might contain toxic concentrations of this sodium cyanide. This then runs the risk of spilling and getting into drinking water supplies or polluting rivers and affecting wildlife. Cyanide has actually been banned in some countries such as Germany and Turkey, and also some US states such as Wisconsin and Montana. Um, and finally, we can't recover rare and useful byproducts using cyanide, such as tellurium. So there are a few case studies worldwide of disastrous tailings collapses which have led to cyanide reaching the environment. One key example is the Baia Mare example from Romania. This is where 100 metres cubed of contaminated liquid spilled into local river systems. This contained 50 to 100 tons of cyanide. It first affected the Somme River, but once it's in the system, it obviously travels. So an isolated spill can have a really long-term effect and large-scale environmental impacts. The spill then affected rivers such as the Tisza and the Danube, and the contamination eventually travelled into the Black Sea. There was an increase in wildlife mortality following this spill, killing thousands of fish, including 20 some protected species. This photo is an example of some of the disastrous after effects. It also poisoned drinking supplies for many local people. So naturally, because of these disasters, the public's perception of cyanide is very poor. While industry cyanide usage is actually typically dealt with very safely, spills such as the Baia Mare mean that a large proportion of the public will be very wary of cyanide, therefore they won't be happy with cyanide operations occurring near them. There was actually a case in Australia where the pushback from the public was so significant that the mining company were driven to cancel their proposal for using this reagent in one of their mines. This was because there was an 85% objection from the public about the use of cyanide and the potential for contaminated tailings reaching their water system. This picture here is from Romania following the disastrous spill, and it shows there's a really low public acceptability there. So this is something that modern mining companies really need to consider when deciding what reagent to use in their operations. So taking all of this into account, there seems to be a real need for a viable alternative to cyanide. One such alternative is Deep Eutectic Solvents, or DES. These have been developed at the University of Leicester, and they are ionic compounds of anhydrous salts, which are liquid at low temperatures. They also boast being environmentally benign and chemically stable, and at low temperatures they can dissolve gold from ore, which can then be recovered by electrolysis. Another advantage is that they have a low vapour pressure, so they don't smell or release any gases, and they're mixed and made from non-toxic, fairly environmentally benign ingredients. Another huge advantage is that they can recover the rare resource tellurium, which is typically a byproduct of the gold processing industry. So now we need to consider how successful are these solvents and reagents, and how do they compare to cyanide? There have been numerous studies from the University of Leicester which suggest a high level of success at extracting gold, silver, and telluride minerals from ores. Additionally, the reagent is effective at low temperatures of 45 to 50 degrees, therefore requiring little energy to operate really efficiently, improving the green credentials of this method. Leaching rates using the reagent have generally proven to be really fast. For example, electrum dissolves up to 40 times faster by DES compared to cyanide. Although the dissolution rate does depend on several other factors such as mineralogy, degree of liberation, etc. A really significant benefit of utilising DES is its ability to selectively dissolve various minerals. For example, tellurides and electrum can be dissolved through an oxidative leach. However, sulfides can be selectively dissolved in a deep eutectic solvent by electrolysis. So finally, I'll just touch on what these deep eutectic solvents are actually made of. So they're eutectic mixtures, which means the mixture has a lower melting point than the individual components, of ammonium salts like choline chloride, as well as urea, which acts as a hydrogen bond donor. One huge benefit is that these components are readily available, as they're already produced in really large quantities. For example, choline chloride is actually produced as a B12 food additive on a megaton scale, and urea is produced as a common fertilizer around the world. These are both relatively cheap components and are relatively non-toxic, biodegradable substances which can be easily and safely disposed of and recycled. So now I'd like to touch a little on the energy problem and why the recovery of the rare resource tellurium is really important to present society. As we're all very aware, global warming is a real crisis, and as part of decarbonising our future, we must find alternative sources of energy to power our lives and make these actually our primary sources of energy. One source of green energy is exploiting solar energy from the sun by using solar panels. However, in order to move from the traditional fossil fuel sources, there are some materials which we must mine in order to operate the renewable resources. One of those is tellurium, a rare mineral that contributes as an essential component to building photovoltaic solar cells. And the global demand for this rare material has surged in the last decade due to continued efforts to increase this proportion of energy that we're producing worldwide from renewable resources rather than coal, oil, and gas. UN agreements such as the Paris Agreement means the demand for this resource is predicted to continue to increase over the next 10 to 15 years. This chart is really here just to show how much the global demand for solar energy has increased and how it shows no signs of slowing down. We can see from 2000 to 2019, the use of solar panel has absolutely skyrocketed, and in order to continue to grow this aspect, we must continue to find and mine these raw materials that are absolutely necessary. And presently, the tellurium demand is met by recovery during copper processing at large high-grade copper deposits like porphyry deposits. However, these deposits are becoming rarer and rarer to discover, and it's becoming less economical to recover the tellurium from these. Therefore, in order to meet the demand, we must find alternative sources of tellurium, and many gold deposits actually have really high tellurium grades, especially those which are epithermal. Now for my research specifically. I'm assessing the success of Deep Eutectic Solvents in the Gold Hill project in Colorado. The Gold Hill project encompasses a few different small-scale inactive mining operations in Gold Hill and Boulder County Silver and Telluride Mining District. This here is a photo of the small town Gold Hill, and mining here actually began with the discovery of placer gold around 160 years ago, and the pinnacle of mining was in the late 1900s. It's estimated that since this time, Boulder County has produced over 1 million ounces of gold, and the majority of this has been sourced from the Gold Hill district, and a great proportion of which is included within this Gold Hill project. So what we're looking to do for this company is prove that Deep Eutectic Solvents can recover a large proportion of these gold and silver telluride minerals from the site. This adds both financial and environmental credentials to the company by recovering the useful tellurium, which would typically be a byproduct. Although I'm yet to complete the leaching experiments, I've gathered some data which can really help predict the success that the DES may have. SEM EDX results and thin section studies have informed mineralogy, some of which is the gold telluride mineral calaverite as shown here. It can also inform textures and allow us to make predictions. I'm interested in everything that you typically are for processing, so the more liberated and exposed the target minerals are, the more likely we are to successfully recover and leach these. And it's important to know what our target minerals are associated with and where the gold, the silver and tellurium is held the most. This work has been really difficult to conduct remotely this year. However, the University of Leicester have really worked with the students so we can still make our projects as great as possible. Here's a photo of me working from home with my transmitted and reflected light microscope delivered by the excellent University of Leicester technical team. So, what is the future of gold processing? Well, I think it's really clear that we need to find an alternative to cyanide. One which is not only more environmentally friendly and has a better public opinion, but that can also recover all of that valuable material and all those necessary resources for us to move forward in the future and develop renewable energy. I think deep eutectic solvents have the potential to solve both of these issues as an environmentally benign, chemically stable reagent which can recover tellurium. If you've got any questions about my talk, feel free to ask me in the Q&A session or email me. My information is on the screen now and I'll try my best to answer. I hope you've learned a little something about tellurium and deep eutectic solvents. Thank you.